Welcome to another video in a series on the xv6 operating system kernel. In this video, I'll cover the console device and textual input and output from the kernel, including the panic function and the printf function, which the kernel uses to print messages. Text input and output goes to and through the UART device. I'll describe how the UART works and how serial communication is performed, and the software that connects the higher level functions with the actual UART device. Let me remark that this part of the xv6 kernel has undergone significant changes and reorganization in the recent past. The structure is now very different from what I described in my previous xv6 video series back in 2022, which is now completely out of date. So in this video, I'll cover the UART device, including memory mapped I/O concepts, the high-level interface, and in particular console read and console write, the tasks of echoing and buffering input, and interrupt handling, as well as the functions panic and printf. In this video, I'll be covering a number of functions with complex interactions. So let's start by showing the function names and the call tree. Here we see the functions I'll be covering, and the green lines indicate which functions call which other functions. For example, UART interrupt calls both console interrupt and UART getC. The main two functions are console read and console write. When the user process makes a read system call or a write system call, and the I/O is to go to the UART device, the functions console read and console write will get called to do the work. Also, the kernel code may call printf to help in debugging. And if there's an error in the kernel, it'll call panic, which will also call printf to print the error message. Printf will call cons put c for each character it wants to print, and cons put c will call UART put c sync, which actually interfaces with the UART device. I'll use red arrows to show how the bytes flow to the UART like this. Printf passes a character to cons put c, which passes it to UART put c sync, which sends it to the UART device. When the user process wants to write, console write will call UART write, and UART write interfaces with the hardware directly and sends the characters to the UART. What about input? Well, the user may have typed something in the past, so there's an input buffer which will hold the characters until they're called for. So console read will get bytes from the buffer if they're there, but if the buffer's empty, console read will have to go to sleep to wait. The UART is a relatively slow device, much slower than software, and it may not be ready to perform output. If the UART is busy sending a previous character, then UART write will have to go to sleep and wait. Then, when the previous output finishes, the device will generate an interrupt, which I'm showing here with this dashed purple line. When the device can accept another character for output, it generates an interrupt, and the interrupt handler will invoke the UART interrupt function. The UART interrupt function will then wake up UART write if it's asleep waiting. Also, when input arrives, when the user presses a key, an interrupt will be generated. So UART interrupt will also call the UART getC function to get a byte from the device if there is one ready to be retrieved. Then UART interrupt will then invoke console interrupt, passing it the new incoming character. Console interrupt will place it in the buffer. Console interrupt will also do two more things. It will wake up console read in case it was asleep waiting for user input, and it will echo the character. It echoes the character, that is, writes it back out so the user can see it, by calling cons put c. Okay, that's our roadmap. Now let's get into the details, starting with the UART device. For xv6, we have two external devices, the disk and the UART. Well, we also have the platform-level interrupt controller, which is also sort of a device. Anyway, all these devices are memory mapped, which means that each occupies a set of addresses in the physical address space. The core moves data to a device using store instructions, and it retrieves data from the device by using load instructions. Let's look at the UART device, which handles serial communication by facilitating a stream of bytes flowing out. These are the transmitted bytes, and bytes flowing in, and these are the received bytes. QEMU will emulate a UART device, and in particular, it will emulate something called the 16550A chip. This chip dates back to the early days of computers. From big multi-core ARM chips to Arduinos and tiny embedded microprocessors, most all modern processors have a built-in UART interface since serial communication is so simple and standardized. Many are still modeled on the 16550A device, but others use slightly different interfaces between the core and the device. QEMU simulates a 16550A device, and it will deliver any bytes transmitted by the kernel to the 16550A device to your laptop screen, or to be more specific, to whatever QEMU's standard output is mapped to. And anything you type in to standard in will be delivered by QEMU to the 16550A device it's emulating, and these bytes can then be retrieved by the xv6 kernel software. Basically, the 16550A works like this. On one side, it has the serial interface. This consists of two wires called transmit and receive, and these each carry a bit stream to somewhere else, such as a display or keyboard. On the other side, the device has a number of so-called I/O registers. The 16550A has 7 registers, and each register is quite small, only 8 bits, that is, 1 byte, in size. These registers are memory mapped, which means that each I/O register lives in the device, but at the same time, it's mapped into an address in the physical address space. The code uses a store instruction to send data to the device by writing into the address assigned to a particular I/O register. Likewise, code can use a load instruction to retrieve data from the device by reading from the address of one of the I/O registers. The device also has the ability to interrupt the core. Next, let me describe the I/O registers of the 16550A, starting with the main two registers, which are called the transmit hold register and the receive hold register. To send a byte, that is to transmit a character to the display, code will store a byte into the transmit hold register, or more precisely, into the memory address into which the transmit hold register is mapped. To get a byte, such as to retrieve a character that has been received from the keyboard, the code will load from the receive hold register. Of course, we also need some synchronization. Transmitting bytes takes time, and the device might not be ready to send the next byte because it's still busy transmitting the previous byte. The code must not try to send bytes too quickly, or data will be lost. As for reading, the next input byte may not be there yet. If the code just loads without waiting, it may retrieve meaningless data. The 16550A has another register called the line status register, or LSR, which you can read to see whether the device is ready. Within it, the bit named LSR receive ready will be 1 if there's a new byte that can be read from the receive hold register. Once retrieved, the bit will go back to 0 until the user types another character. The bit named LSR transmit idle will be 1 if the UART has finished transmitting the last byte and is ready to send another byte. Writing to the transmit hold register will cause this bit to become 0 until the device completes the transmission. So, one approach, used in places by xv6, is to just loop, testing these bits repeatedly, over and over, until the device becomes ready for the operation. But such spin loops are obviously wasteful. Fortunately, the device is also able to interrupt the core whenever a transmission completes. This allows the core to do other stuff and only interact with the UART device when there's something useful that can be done. So, once a new input character has been completely received by the the device will interrupt the core to let it know that there is now a byte that may be retrieved. Likewise, the device may be busy transmitting the last byte to the display and not yet ready for the next byte. But after the transmit completes and the device is ready for a new byte, it will cause an interrupt to let the core know that it is now ready to send the next character. This interrupting behavior is optional, and it can be configured at startup to cause the 16550A to generate interrupts. And in xv6, we'll want that. So there's another I/O register called the interrupt enable register, which contains 2 bits of importance. One bit will be set at startup to enable interrupts to be generated whenever a new byte is received. The other bit will be set to enable interrupts whenever the device is done sending the last byte and able to take a new byte for transmission. Now there's an additional feature of the 16550A. The device also contains 2 internal FIFO buffers to buffer and smooth out transmission. You can more or less ignore these FIFO queues, but I want to mention them. One is a small FIFO queue of bytes that have been passed by code to the device. These bytes are queued up and waiting for transmission. The device also contains another FIFO buffer on the receiving side. This contains characters that have been typed but not yet received by the code. On the input side, the buffering might prevent data loss if the core cannot respond quickly enough to retrieving incoming data. On the output side, the buffering can increase performance by allowing many bytes to be sent in one burst in a loop, rather than requiring interrupt processing for each byte. There's a control register called the FIFO control register, which we will initialize to enable these 2 FIFO buffers. Even though they're there, you can pretty much ignore these FIFO queues. We also need to initialize the UART device for the baud rate and details like whether we are using a parity bit or not. This is done with a register called the line control register. The code initializes the 16550A to communicate at 38,400 baud, 8 bits, no parity, and with 1 stop bit. These are details about the bit transmission for serial communication. But frankly, QEMU is going to ignore all this, and all these bytes are just going to go directly to standard in and standard out. Recall that the UART device is mapped into address hex 10000000. The symbol UART0 is defined to be this address. The I/O registers are located at small offsets from this address as shown here. Notice that some registers share the same address. For example, the transmit register and the receive register are both mapped into the first byte at offset 0. If you store into this byte, you are writing to the transmit hold register. And if you load from this address, you are retrieving data from the receive hold register. Here we have some defines for the various registers associated with the UART. We see the receive hold register, the transmit hold register, the interrupt enable register, and definitions for the 2 bits in it that we care about. The FIFO control register, and a couple of bits that we'll need to initialize. The interrupt status register, the line control register, and the bits that we need for that. And finally, the line status register, along with the bit that tells whether we have received an input character and the bit that tells whether the device is ready to transmit another byte. This macro function, named reg, is used to combine the offset of the register with the base address of UART0 to give the address of the byte, as well as casting it into a pointer to a byte. Then we have 2 helper functions. readReg is used to generate the load instruction, given the symbolic name of the relevant I/O register. It returns the byte. And the writeReg function is used to generate a store, given the name of the register you want to store into, along with the byte to write to it. Here's the code for the function UART init, which is called once at startup. First, we write to the interrupt enable register to prevent interrupts while we're initializing things. Then these 4 statements write to the I/O registers to set the baud rate and parity stuff. Then we write to the FIFO control register to enable the internal buffers in the device. Then we write to the interrupt enable register to enable interrupts, which will set up the device to generate an interrupt anytime the kernel can send another byte to the output or retrieve another byte from the input. And finally, we initialize a spin lock called txlock. Next, let's talk about this Boolean flag named txBusy or transmit busy. Whenever we send a byte to the UART by writing to the transmit hold register, the device becomes busy sending the character. We need to wait before we write the next byte, or else data loss can occur. We must not send bytes to the UART before it's ready to receive them. So we set txBusy to true whenever we move a byte to the UART. Then the sending process needs to wait before sending the next byte. Later, when the UART becomes ready to accept the next byte, it'll cause an interrupt, and the interrupt handler will clear the txBusy flag and wake up whatever process is waiting to send more bytes. xv6 uses the sleep and wake up functions to control this, and I'm assuming you watched my video on those and know all about them. The spin lock, named txlock, protects the txBusy flag. To examine or modify txBusy, we must first acquire and hold txlock. Also, we've got this thing called txchan. It's defined as a variable, but we never use it that way. Nothing is ever stored into it. Instead, it exists only so we can use it, or more precisely, use the address of this variable as the channel number on which we will be sleeping when the UART is busy sending and the txBusy flag is set to 1. So, whenever we clear txBusy to 0, we'll do a wake up using txchan. Okay, now let's look at UART write, which is used to send a bunch of bytes. It's passed buff, a pointer to some characters in memory, along with a count n of how many bytes to send. And it has a loop, and it goes through the buffer using I as an index. Down here, we send byte number I by getting it from the buffer and writing it to the transmit hold register in the UART device. Then we increment I, set txBusy, since the UART will now be busy sending that byte, and loop back until all bytes have been sent. Up here, before we can send the next byte, we have a loop that waits for txBusy to become false before we can do the sending. Whenever we examine or modify txBusy, we need to be holding the spin lock that protects it. So up here, before anything, we acquire txlock, which protects txBusy. Then we see the classic pattern of sleeping. If txBusy is true, we need to wait before sending. We reach this loop holding the lock, and we check txBusy. If the UART is busy, we need to sleep. So we call sleep, passing it a pointer to the spin lock and to the channel. txchan is that dummy variable whose address we are using just for our channel number. While sleeping, the lock is released, but after this process gets woken back up, the lock will be reacquired before we continue. Whenever the UART becomes ready to send another byte, it'll cause an interrupt, and a call to wake up will be made. This will wake up this process and will loop back up to see if the UART really is now ready by again checking txBusy. Of course, if several processes are sending bytes, several processes are concurrently executing UART write, and they'll all get woken up. So there's going to be competition, and one of the processes will grab the lock first and send another byte. The output, all the characters from the different processes, will be interleaved, and the output could be a real mess to read. So if more than one process is writing to the console device, nothing prevents arbitrary interleaving of output characters. Finally, after all bytes are sent, we release the lock and return. The approach taken here is simple, and it works just fine. But I feel compelled to mention that this design fails to utilize the FIFO queue on the 16550A chip. This code always puts only a single character in the FIFO queue. Then it sets txBusy and waits until it's sent, and the FIFO queue is once again empty. It never puts more than one byte at a time into the FIFO queue, and it has an interrupt after each byte is transmitted. Technically, the 16550A interrupts only when the FIFO queue becomes completely empty, not after each character is sent. But since we only put one character at a time into the FIFO queue, we get an interrupt after each character is sent. To fully utilize the FIFO queue, we'd need to make this code a bit more complex. A more efficient design would, after each interrupt, fill the entire FIFO queue instead of writing just one character to it. The next interrupt would not occur until after all characters were sent and the queue is once again completely empty. This would result in many fewer interrupts, and the character interleaving problem would still occur, but less often. But the approach taken here works just fine. Now let's see how the UART write function is used. When a user process writes to something like standard out, the bytes might go to a disk file, or they might go to a device. One device is traditionally called the console, which for xv6 is just the UART. Crucially, the bytes to be written out come from the user's virtual address space, and to deal with that, there's a kernel function called console write, shown here. Console write is passed source, which is a virtual address, and n, which is the number of bytes to be sent. Basically, console write will move bytes from the virtual address space into a kernel buffer and then call UART write to send what's in that buffer to the UART. This parameter, user source, is a Boolean, and it's true if this is a virtual address space, which it always will be. Here's that buffer, which contains up to 32 bytes. Here, we call the function either copy n. Either copy n will move bytes from the user's virtual address space to a kernel area. Buff is the address of our buffer, and source plus I is the virtual address telling where to get the bytes. User source is a Boolean that indicates whether or not the source address is a virtual or a physical address. And as I said, it will always be true to indicate that we are getting bytes from the virtual address space. Since our buffer is only 32 bytes, we'll need to break the task up into chunks of at most 32 bytes. NN is the number of bytes in each such chunk. We have a local variable, I, telling how many bytes we've written out so far, and it starts at 0. This loop says, while we have not yet written all n bytes out, keep going. Then we write out nn bytes. So first we try to write out a full 32 bytes, which is the size of the buffer. N minus I is the number of bytes left to be written out, and if we have less than 32 bytes left to write, then we'll just write out whatever is left, so we reduce nn to that. Then we call either copy n to move nn bytes into the local buffer. If problems occur, such as a page fault, it'll return -1 and we abort the loop. But otherwise, we call UART write to send those bytes to the UART. Then we increment I and loop back for the next chunk. Finally, we return the number of bytes we successfully transmitted. To recap, the way xv6 handles output to the UART is this. In the quiescent state, when no output is happening, the FIFO queue on the chip is empty and the txbusy flag is false. When a process wants to send a byte, it waits until txbusy is false, then writes the byte to the UART device, and at the same time sets txbusy to true. The UART immediately begins sending the byte, which could take a really long time relative to RISC-V execution speed. If there are more characters to be sent, the process will go to sleep, waiting for txbusy to become false again. As I said a second ago, the code doesn't go ahead and fill up the chip's FIFO queue. It only sends one byte at a time, so the FIFO queue is not fully utilized. Later, after the sending of that byte is complete, the FIFO buffer will once again become empty. That'll cause the UART to signal an interrupt. The interrupt handler will then set txbusy back to false and wake up any processes waiting on it. Now let's look at the UART interrupt handler that does that. First, in dev enter, we check to see what caused the interrupt. If it was the UART device, we invoke a function called UART enter or UART interrupt. So now let's go over the code in the UART interrupt function. It begins by reading the interrupt status register. Loading from this register will let the 16550A know that the interrupt has been recognized and is getting handled. It's basically an acknowledgement which causes the UART chip to lower its interrupt request line. Now, the interrupt could have been caused because the transmit side is ready to send another byte, or it could have been caused because an input character has been received, or both. First, we read the line status register and check the transmit idle flag in it. If it's 1, that means the output is done. The device is finished transmitting, and the output FIFO is once again empty. We're now ready to send the next output byte, so we clear the TXBusy flag. But of course, this flag is protected by a lock, so we first acquire that lock, and then after we're done, we release the lock. Also, if we just set TXBusy to false, we need to wake up any processes that are waiting to transmit bytes. By holding the lock when we fetch the status bit, we're preventing processes from simultaneously transmitting bytes, which might affect the status bit. Recall that in UART write, we were holding the lock at the moment we wrote into the transmit hold register. After waking up any and all processes waiting to write, we release the lock. After dealing with the transmit side, we turn our attention to the receive side and process any incoming bytes from the keyboard. This loop calls UART get C repeatedly. Each call retrieves and returns the next received byte. If there is no byte on the input, that is, if the user has not pressed a key and we've already retrieved every byte that came in previously, then UART get C will return -1. For each received character, we call the function console enter or console interrupt, passing the byte that just came in. And we keep fetching characters until there are no more waiting to be retrieved, and UART get C returns -1. Next, let's look at UART get C. It's simple. It checks a status bit to see if there's a new byte that's come in. And to do this, it reads the line status register and checks the receive ready bit. This bit will be true if there's a byte that's been received from outside, but not yet fetched from the receive hold register. If so, we grab the byte by reading the receive hold register and return it. The act of reading this register will clear the ready bit in the status register. Well, the chip has a FIFO queue for the input, so actually there might be another byte immediately ready to be read if there were several bytes sitting in the queue. But anyway, if the user has not typed anything and there was no byte there, we just return -1, which causes that read loop in the UART enter function to terminate. The next question is, what do we do with the incoming byte? We need to do two things. First, we need to add it to the kernel's input buffer to hold it until the user process asks for data. Second, we need to echo the byte. The console interrupt function will do these things. But first, let's look at a function called consputC, which will be called to echo the character. The idea is that whenever the user types any character over a UART connection, the software has to echo the character back. Merely pressing the key does not cause anything to appear on the screen. Instead, it has to be explicitly echoed by software to be visible. And consputC is used for performing this echoing. There is one gotcha, and that's that the backspace key, that's the delete or erase key, has to be echoed specially. If the character to be echoed is not a backspace, we simply echo it by calling a function named UARTputC sync. Sending the backspace character to a typical serial terminal only moves the cursor. It does not actually erase the previous character. So backspace is traditionally echoed with 3 bytes. To echo the backspace character, this code will output 3 characters. First, it will back up, placing the cursor on top of the last character. Then it will display a blank character, which overwrites the bad character, advancing the cursor. And finally, it backs up again, so now the next character to be typed will go exactly where the bad character was. Of course, we're all used to typing on smartphones and even speech input, and you're probably rolling your eyes. But this is the way serial terminals have worked since long before smartphones, and probably you were ever born. Okay, but what is UART putc sync? Let's take a look at that function. UART putc sync is only called by cons putc. Now, cons putc is used for 2 things. First, cons putc will be used to echo input characters, and second, cons putc is the function that printf will be using to produce output. As the comment says, it's used to write bytes, and it's used by printf and to echo characters. And crucially, it says without using interrupts. It spins while waiting for the UART to become ready to accept the next output character. It's past C, the character to be printed, and skipping down to here, we see that it has a loop. It reads the status register and checks the bit that tells whether the UART device can accept the next output character. If not, it spins, waiting until that bit becomes true, and then it simply stores the byte into the UART's transmit register. To explain this stuff here, we first need to talk about what happens when the kernel detects a bug and calls panic. So here's the panic function. It's passed an error message, and first the panic function sets a Boolean flag called panicking to true. Then it prints the error message using printfs, and then after the error message has been printed, it sets a second flag called panicked to true. The purpose of this flag is to stop all further output, so the panic message is the last thing printed. Then it freezes this process by going into an infinite loop. Now let's go back to UART putc sync. So if we've had a call to panic somewhere else, and the previous error message has finished printing, and we're now in this function trying to print something, we'll see that panicked has been set to true. So we'll just lock up this core by going into an infinite loop. The purpose of this is to make sure that a previously printed kernel error message is not buried under a lot of subsequent output. Also, at the top of this function, we disable interrupts with a call to push off, and after we're done, we re-enable them with a corresponding call to pop off. Actually, these calls are totally useless. They do nothing, and both calls should be removed. UART putc sync is called only from cons putc, and cons putc is called in only 2 situations. First, it's called to echo input characters. Echoing is done within the interrupt handler, so interrupts will already be disabled. And second, it's called from within printf, which the kernel uses to print messages, and printf begins by obtaining a spin lock. Acquiring a spin lock disables interrupts. So again, interrupts will already be disabled whenever we enter UART putc sync. Therefore, the calls to push off and pop off are pointless. My guess is that this is a historical artifact left over from prior program development and debugging, which happens. Notice that if interrupts were enabled, and a timer interrupt were to happen between checking the status bit and the actual sending of the byte, a bunch of stuff could happen, and by the time we get around to sending the byte, the status might have changed and no longer be the same. Also, in a multi-core system, of course, disabling interrupts doesn't stop other cores. Disabling interrupts is just not the correct way to synchronize. Anyway, just ignore the calls to push off and pop off. Maybe they'll be gone by the time you watch this video. Next, let's talk about input. At more or less random times, the user will type on the keyboard and an input byte will come in through the UART device. When there's a byte that's been received by the UART and is ready to be retrieved by the software, the 16550A will signal an interrupt. The interrupt handler will run and retrieve the byte. But then, what will it do with it? Maybe the user program has not yet made a read system call. The answer is that the kernel maintains an input FIFO buffer. This is not to be confused with the FIFO buffer on the 16550A itself. Both FIFO queues exist. The UART chip's FIFO holds input characters until the software interrupt handler gets around to retrieving them, and the kernel's FIFO queue holds input characters until the user process gets around to retrieving them. So let's look at the kernel's buffer, which is defined here. It has a size, which is defined to be 128 bytes. And here's a byte array called buff, which is the FIFO buffer of 128 bytes. Then we have three indexes into this buffer: R, W, and E for read, write, and edit. All three are implicitly initialized to 0. The buffer and the pointers are all protected by a lock called simply lock, and all of these are grouped into a structure named cons. Here's a diagram showing this buffer. Normally with a FIFO queue, we only need two indexes. The read index tells where to read from, and that's the R index. That is, to retrieve a byte, we go to the position indicated by R and get the byte there, and then increment R to point to the next buffer element. The other index tells where to write to. In this diagram, that's the E index. So to add a byte to the buffer, we use the E index, and we write a byte to that position and then advance the index. Of course, the buffer is shared by multiple processes, so we have to acquire the lock whenever we want to add or retrieve from the buffer. Before I talk about the W index, let me get a couple of points out of the way. First, if the R and E indexes are equal, it means the buffer is empty. The next addition to the buffer would be at E, the same position that the next read would come from. So the test, R equals E, determines if the buffer is empty. Next, the buffer has a limited capacity and is a wraparound buffer. We keep incrementing the indexes even after they get much larger than 128 bytes. But before using any of them as an index into the array, we take the index modulo the buffer size. This allows us to keep incrementing the indexes forever without needing to constantly check anything. Now, of course, continual incrementing will eventually cause an overflow of these indexes, which are unsigned 32-bit numbers. xv6 doesn't bother to check for overflow, and it will fail when that happens. But it seems reasonable to ignore this, since it'll only occur after 4 gigabytes of user I/O, which is a lot of bytes and unlikely to happen in practice. The number of bytes in the buffer is E minus R, so we can test whether the buffer is full very simply by asking whether E minus R is equal to the buffer size. When that's true, the buffer contains 128 bytes and there is no more room. Now what about the index named W? In Unix and Linux, there are two modes for input from a keyboard: cooked and raw. The difference between cooked and raw modes is a whole can of worms that I do not want to open in this video. But basically, cooked mode echoes the keystrokes, and it also allows the user to edit the typed input before the software gets it. And to support this editing, the kernel buffers the entire line until the return or enter key is pressed. In raw mode, each keystroke is passed to the user process immediately, and the user process is responsible for everything, including echoing. xv6 implements only cooked mode. What this means is that the xv6 kernel will take care of echoing each keystroke as it is pressed, and the processing of backspace keys, and will also allow the entire line to be canceled with the Ctrl-U key. Also, it'll give complete lines to the user, buffering all input until the user types a return or enter key, or enters a Ctrl-D to indicate end of file. To implement this, the W index points to the byte just after the last new line character. Each time the user does a read system call, the kernel will return the next line of input, that is, all bytes up to the new line. And if the user types a control U, the kernel will backspace over all the bytes entered after the most recent new line. In summary, the W index points to the byte just after the most recent new line. Okay, now let's look at how user input is processed. Whenever the interrupt handler, that's UART interrupt, sees a new byte coming in, it calls console interrupt to put that byte into the console buffer. Here's the console interrupt function, which is passed the incoming character. First, it acquires the lock on the buffer. Then it looks at the byte with this switch statement and adds it to the buffer. Then down here, it releases the lock and returns. Let's go through these cases. This C macro is just used as shorthand for Control P, Control U, Control H, and so on. First of all, Control P is handled specially. Whenever the user hits this key, the kernel immediately prints information about all processes, and the character is not added to the buffer. Instead, we just call proc dump to print out a list of all current processes, which might be helpful in debugging the kernel, and then return. We break out of the switch, release the lock, and return. Next, let's look at this case. Some terminals differentiate between a backspace key, which sends Control H, and the delete key, which sends the ASCII code hex 7F. In either case, we do backspace processing. We check whether the E index and the W index are the same. E points to the next free spot, and W points to the next element after the last new line. If they're equal, that means no bytes have been added since the last new line, so we simply ignore the attempt to backspace. Otherwise, we back the E index up and send that 3-byte sequence, backspace, space, backspace, to the UART. Now let's look at what happens when the user types Control U. We have a loop that just does a bunch of backspacing, just removing a bunch of bytes from the end of the buffer, like the single backspace key did. And we keep backspacing until we either get to the point where E and W are equal, or to the point where we see that the byte before this point is a new line, which would make E and W equal anyway. In other words, we delete all bytes after the W index position and after the most recent new line. Now let's look at the default case, which handles all normal characters as well as new line and Control D. First, we check whether it's the null character code or whether the buffer is completely full. In either case, we simply ignore it, effectively dropping the character. To get the number of bytes currently in the buffer, we subtract the position of the first byte, that's R, from the first empty position, which is E. If that is less than the size of the buffer, then we have at least one empty slot remaining. The return or enter keys can send either an ASCII return code or a new line code. If it sent the return code, which is \R, we immediately mutate it into a new line. Then we echo the character, whatever it was. Next, we store it in the buffer at position E and then advance the E index. Finally, if we just added a new line or a Control D to the buffer, we need to wake up any processes that are waiting. The user's typed a full line, and we can now make it available to the user process. Also, if the buffer is full, we also need to wake up the process. If the buffer is full, we can't just wait until the user hits a new line key, since there's no place now to store it, and we just ignore it. So, if the buffer's full, we sort of pretend that a new line has been entered and give the user whatever is in there, possibly not terminated by a new line. And we also update the W index to point to the next free position, that is the element right after the new line, or Control D. Finally, we wake up any and all processes that are waiting for input from the UART. The channel that sleeping processes use is the address of the R index variable. So that's it for dealing with the newly received incoming byte. So we release the lock and return. Now let's look at the function console read. Whenever the user process executes a read system call and the data is to come from the UART, this function will be invoked. It's passed destination, which is the location in the virtual address space where the data should be placed, and n, which is the maximum number of bytes to read in. The user destination argument will always be true, indicating that this is a virtual address and not a physical address. We're going to get data out of the buffer, so we begin by acquiring the lock. Then, after we're done, we release the lock and return the number of bytes we actually read. Each iteration of this while loop will take one byte out of the buffer and move it into the virtual address space. We use the either copy out function to move the byte into the virtual address space. Destination is the destination address, and we increment it after the move. And this 1 is the byte count, so we move 1 byte at a time. We've got two local variables, c and cbuf. C is an integer, and cbuf is a byte. Up here, we get the byte and put it into the integer variable. We are reading using the R index and incrementing it afterwards. And here, we move it into the byte size variable. Now, I'm not exactly sure why we bother with the integer size variable, but this code does. Anyway, for the either copy out, we provide the address of the byte-sized variable. If this copy fails, for example, if the virtual address was invalid, we immediately abort and terminate the loop. Up at the top, we saved the original number of bytes we are looking to copy in a variable called target. Whenever we copy a byte, we decrement n. So then, down at the bottom, we do the subtraction to determine the number of bytes we successfully copied into the user's virtual address space and return that number. So this loop keeps repeating until the number left to retrieve from the buffer becomes 0, or we stop copying for some other reason, such as an invalid virtual address. Now, before we can remove a character from the buffer, we need to make sure there's actually something there, and that's what this while loop is all about. We're going to stop copying when we reach the W index, which tells us where the new line is. So we first check to see if there's anything in the buffer. R points to where to get the first character, and W points to the position after the new line. So we need to stop after we copy the thing before W. If R and W are equal, then there's nothing to copy, so we need to wait until there is. So we go to sleep, using the address of the R index as the channel. Previously, we saw how we used that for the wake-up call, and passing the relevant lock. It's possible that someone has set our killed flag, so before we go to sleep, we check that. If we've been told to commit suicide, we immediately release the lock and return. The calling code will take care of calling kexit, so this return value will end up getting ignored since the read system call will never return. Then we extract the next byte from the buffer and increment R. Then we ask whether it was a control D, the end of file code. If so, we break out of the loop before we move it into the user's virtual address space. To indicate an end of file, the kernel will return a byte count of 0. But if there are characters before the control D, we need to return them first. So there are two possibilities. In one case, the users entered a bunch of characters followed by a control D instead of a new line. In that case, we need to first return all those characters before letting the user know about the control D. So in that case, we'll ignore the control D for now and just return a non-zero count. But we don't want to forget the control D. So that's why we back up R. So next time, we'll see the control D again as the first thing. The other case is that the user has typed control D without first typing anything else. In that case, we want to return 0, which will indicate the end of file to the user process. So if on entry to this function, R points to the control D, then on the first loop iteration, we'll see the control D. We haven't yet decremented n, so n still equals target. So R is advanced, and we don't back it up. We just break and return. We'll let the user know that there was an EOF by returning 0, which happens when we subtract target minus n. And since they're equal, that's 0. After that, the user can continue to enter more lines, and these will be processed as normal. So this subtraction computes how many characters were moved into the user's space. If none, then n will still be equal to target, and we'll return 0. But if we've already moved any other characters into the user space, then n will have been decremented. If the user ended the line with a control D instead of a new line, we will save the control D for next time. By decrementing R, it'll leave us positioned on the control D. R will point to the control D byte, so it'll be the first thing we see on the next read system call. And at that time, we will have moved 0 bytes, so we will return 0. In either case, we're done, so we break out of the loop. If it wasn't a control D, we go on and copy it into the user space. Then we ask, did we just copy the new line character? If so, we're done, so we break out of the loop. So regardless of whether or not we've reached the desired byte count, we exit. We release the lock and return the number of bytes we actually copied into the user's address space. Next, I want to go over the file printf.c. This file contains the printf function and a couple of helper functions it uses. Elsewhere in the kernel, we only call printf, not the helper functions. So printf is the external interface, if you will. This printf is unlike the printf that user processes use. For user processes, printf uses the write system call, which sends the output to standard out, which can be mapped to either the console device or a file or possibly a pipe. For the kernel, this version of printf outputs differently. It calls cons put c for all printing, which sends the bytes directly to the UART. So this function implements a version of the printf function. It uses only cons put c, which it calls for every character it wants to print. Now, it's possible that several processes are calling printf concurrently. Without any synchronization, the output bytes would be completely interleaved and virtually impossible to read. However, we have this lock here. Each call to printf will acquire and hold this lock while it's producing output, and then release it when it's done. So this effectively makes each printf statement atomic. So as long as everything you want to print is within one printf, it will be printed together as one unit without interleaving from other processes. Each call to printf executes to completion before any other printf can start. So here's the printf function, and you can see it begins by acquiring this lock, and down at the bottom, it releases the lock before returning. However, if the kernel has a bug, it's possible that acquiring the lock could get us into an infinite loop, spinning forever. This would definitely happen if the bug occurred in printf itself, since the lock would already have been acquired. If we're trying to print out a message due to a kernel bug, we really want to see that message. So we throw caution to the wind. If panic has been called, that is, if panicking is true, then we avoid waiting to get the lock and just start printing. As you know, printf takes a variable number of arguments. The first is the format string here, and the ... is how you indicate to C that there can be 0 or more arguments after that. To deal with a variable number of arguments, C uses a VA list. So here we have a variable argument list thing called AP. We need to invoke a function called VAStart before anything. Then, periodically, we call VARG, like here and here, to get each argument in turn when we need it. So this loop is going to go through the format string, character by character, using I as an index. I starts at 0 and gets incremented each time. And here we extract the ith byte from the format string and store it in an integer variable called CX. If we're looking at the null byte, which marks the end of the string, we're done. So the loop terminates and we release the lock and return. The first thing we do is ask if it is a %sign, which signifies a formatting code. If not, we print the character by calling cons put c, and we're done. The continue just moves on to the next loop iteration, and we look at the next character. Otherwise, we have a percent sign, so we increment I to skip past it. Then we grab the next character after the percent and put it in C0. For example, if the format code is %D, that would be the D. We could end up having 3 format characters following the percent, as in %LLD. So we also grab the next 2 characters as well, putting them in C1 and C2. We need to deal with the possibility that the string might end prematurely and not even contain these bytes. And if that happens, we'll just set C0, C1, and C2 to the null character. So, if when we grabbed C0 we got something besides null, we keep going and grab the next byte, C1. And if we still haven't seen the end of string and got something besides null, we grab the third character. Otherwise, they stay set to null. We won't increment I for C1 and C2 until we know that they are actually present. Then we have this giant if statement where we see what format code or codes we have, and we do the appropriate thing. For example, is it just a D? Or is it an L followed by a D? Or is it an L followed by an L followed by a D? Or a U? And so on. Let's start with a D, which means grab the next argument and print it in decimal. So we call VARG with AP and a type of integer. This will return the next available argument as an integer. Then we call a helper function named printint, passing it the value and 10 to indicate that we want decimal output, and 1 to indicate that the value is a signed number and we want to print negative numbers using a minus sign. I'll go over printint in a moment. Next, let's look at the format code LD, which we use to print 64-bit values in decimal. So again, we use VARG to get the next argument, but this time we say to fetch a 64-bit integer. Printint's argument is a signed 64-bit integer, so we have an implicit conversion from unsigned to signed happening here. But just as before, we print it in decimal using a minus sign if it's negative. And also, since the format code was 2 characters, we need to increment I past the second character. For LLD, we have exactly the same code, since both long integers and long integers are the same size and printed the same way. But we have to increment I by 2 instead of 1 this time. We've also got format codes U, LU, and LLU. We handle these the exact same way as we did for signed, except we pass a 0 to the printint function instead of a 1 to indicate that we're dealing with unsigned numbers. Next, we have X, LX, and LLX. These are also handled the same way, except we want to print the number in hex, not decimal. So we pass printint 16 instead of 10 to indicate this, and 0 since we do not want any minus signs. Then we have a format code of P, which is used to print 64-bit values in hex. This time we call print pointer to do the work. It starts by printing 0x, and then it will print all 16 hex digits, so it prints a double word, including leading zeros. This is particularly useful for printing pointers, thus the format code of P. Then we deal with a format of %C, which will look at the next thing and interpret it as a character, which it will print. So we call VARG to get an integer argument, and then we send it straight to the UART by calling cons putC with that value. Next, we deal with %S, which is for strings. We call VARG to get the next thing, treating it as a pointer to bytes. So S points to the string to print. If the pointer itself is null, we'll print this string instead. Then we have a loop that runs through the string until it reaches the null byte, sending each one to cons putC. Next, we check for %%, and if we see that, we are escaping the percent sign, so we just print a percent sign. If we saw a percent sign right at the end of the string, so there was no format code, well, this would be an error. We just break out of the loop. Otherwise, we have some format code that we don't recognize, so we just print whatever it was, preceded by a percent sign. Then, after we've reached the end of the format string, we release the lock and return. We also call VA end to tidy up. This is required by the standard, but it's really a no-op. Now, obviously, this is a simplified version of the real Unix printf, where there's a god-awful amount of complexity in the format codes. But this version is really all we'll ever need for kernel debugging. Also, in real Unix, printf returns the number of bytes printed and sets error no if problems. But since there are no error conditions, this design simply returns 0. Now let's take a look at this helper function printint. It's passed a 64-bit value and the base, either 10 or 16, that we want to use, and a flag that tells whether we should interpret the value as either a signed or unsigned number. This code is really pretty clever and worth going through carefully. Up here on entry, sign is a Boolean telling whether or not the incoming value is to be interpreted as a signed number or an unsigned number. But down here, sign tells whether or not we need to print a minus sign. Also, the value passed in is initially interpreted as signed. Here we copy the number to x, which is an unsigned, that is, a positive value, and x is what we will actually be printing. So if sign comes in as false, we stop right there and immediately use, for x, whatever 64-bit value was passed in. But if sign comes in as true, then it means XX is a signed number and might be negative. So then we ask whether it is a negative value. If so, we negate the negative number to get the positive value and store that in X. If the incoming value is not negative, then we'll use it as is without negating it. But in either case, with signed values, we now set sign to indicate whether or not we need to print the minus sign. And notice that if sign was initially false, indicating that we are to be printing an unsigned value, then after this sign will still be false, meaning do not print a minus sign. Now I should mention that whenever you negate a signed number, it will fail when the value being negated is the most negative number. Negating the most negative number results in the very same value, no change. But when we convert that value to an unsigned number, it will become exactly the positive number that we need to print. So even that edge case is handled correctly. Okay, so now x is an unsigned and thus positive value, and we're going to go through it in a loop from the least significant end to the most significant. In other words, from right to left. As we determine what the digits are, we'll save them in a local buffer, so later we can print them out from most significant to least significant, which is what we really want. So I will index through the buffer, and it starts at 0 and gets incremented each time we store a character into the buffer. Imagine that we're wanting decimal, so base is 10. In each iteration, we take the value modulo 10, which gives us the least significant digit. Then we convert that value, 0 to 9, to a character by looking it up in this array called digits. That's defined up here. Then we store the character in the buffer and increment I. To move to the next digit, we divide by 10 with truncation. So that essentially shifts the value to the right one digit, and we set x to the new value, that is, to the remaining digits. If the new value is now 0, we exit the loop. And notice that by using a do-while loop, we'll always add at least one character to the buffer. So if the value was 0, we'll put only that in. If base is 16, it works exactly the same way, except we are taking things modulo 16 and shifting by dividing by 16. Then we look at the sign, and if a minus sign is needed, we also add that to the buffer. I is now the number of characters in the buffer. Finally, we print the buffer in reverse order from most significant end, or the minus sign if we have one, down to the least significant digit. I think this is really pretty tight code, and if you didn't follow all that, you might want to pause the video right here. Finally, we have the print pointer helper function, which prints a 64-bit value in hex. It begins by printing the 0 and the x. Each 4-bit chunk of the value will cause a single hex character to be printed. Thus, since we have a 64-bit value, we will be printing 16 hex digits. In this loop, we go through the value 4 bits at a time. The size of a 64-bit value is 8 bytes, and 8 times 2 is 16. So this loop runs with I going from 0 to 15 for 16 iterations. We're working from most significant end to least significant. So for each iteration, we shift the value to the left by 4 bits. Then, in the body of the loop, we print whatever hex digit is now in the upper 4 bits. 8 times 8 is 64, minus 4 is 60. So this shifts the upper 4 bits all the way to the least significant end, giving a value between 0 and 15. Then we use that digits array up above to convert those 4 bits into a character code, which we print. Okay, before I sign off, there is one more very subtle point about synchronization that I'd like to discuss. Now, if at this point your brain is full, feel free to stop here. I've covered all you really need to know about the UART. But if you want to dive deeper, stay with me. When sending data to the UART to be transmitted, we need to have some form of synchronization and control to make sure we don't send data faster than the UART can accept it. We have 2 different functions writing to the UART, and they use 2 different ways of doing this flow control and synchronizing. UART write used a flag called txbusy and its associated lock. You could only write when txbusy was false, and when writing, it is set to true. Later, when the transmission completed, the interrupt handler would clear the txbusy flag to false and wake up any processes that are waiting for that. On the other hand, the UART putC sync function completely ignored this flag and directly checked the bit in the UART status register. If the UART was ready to take another byte, the function would send the byte straight to the UART. Here's the problem. Imagine that UART putC sync looks at the status register and decides it's okay to write a byte. But between checking the status bit and writing the byte, the UART write function can sneak in and write its byte first, thereby changing the status before UART putC sync can do its write. But remember, the status bit tells whether or not the FIFO queue is completely empty. So even if UART write snuck in and wrote a byte before UART putC sync could write its byte, there's still a lot of room left in the FIFO queue, so both characters will go in and nothing would be lost. Now, what if you had several processes all executing UART putC sync simultaneously? Couldn't they all check the status bit at the same time and all find that it's okay to proceed, and then all write bytes to the UART at once, overwhelming its internal FIFO queue? No, and here's why. UART putC sync is only called in 2 places, to echo input and for printf. In the case of echoing input, this is done in console interrupt, and at the beginning of that function, we acquire cons lock, and we must be holding it before we can call UART putC sync to do the echo. So only one process at a time can be echoing. In the case of printf, that function begins by acquiring the print lock. So whenever it calls UART putC sync, the print lock will be held. So only one process at a time can be printing in printf. Thus, we can have at most only 3 bytes in the FIFO queue at any one time. One from a call to UART write, one from a call to UART put C sync while echoing, and one from a call to UART put C sync within printf. And the 16550A can handle this without losing data. Now, of course, when panicking, we don't acquire the print lock. So if we had many cores simultaneously panicking, we could, at least in theory, overflow the FIFO queue and have dropped characters. So there is that. A more serious problem occurs when echoing input characters, while at the same time some process is writing to the console. So one process is using UART write. Meanwhile, the user hits a key and console interrupt will call UART put C sync to echo the byte. This is not normally a problem. Of course, the order in which the characters are transmitted could be anything. The interleaving will be influenced by the timing of the keystrokes relative to the process doing the other output. However, there is one situation that can cause a problem, and that's a backspace. Imagine that one process is printing a bunch of stuff while the user is typing. Now imagine that the user suddenly hits the delete key. That will be echoed with the backspace, space, backspace sequence. But since there is no synchronization, these bytes could and would be interleaved with the other output, possibly resulting in the wrong character being obliterated. This problem is pretty inevitable if you think about it. Imagine that the user types a character, say X, and then waits. While waiting, some other process outputs 1,000 characters on the screen. Then, after that X has now been followed by all this other output, the user decides to hit the delete key. xv6 will erase whatever character was last output, not the original X that the user typed. Also, for the backspace, space, backspace sequence to function correctly, these 3 bytes must be contiguous without interleaving, and with xv6, this is not guaranteed. So hitting the delete key while other output is being displayed may not work correctly in xv6. For example, assume that some process is printing the alphabet A through Z, while at the same time the user types X and then hits the delete key. So here's what gets sent to the UART. And here's what the user sees. The F and the L are gone, while the X remains. And we see that space. Okay, there, I got that off my chest. If that didn't make any sense, don't worry about it. The takeaway is that synchronization and concurrency control are very difficult and highly unintuitive. Such programs require very careful reasoning to get correct. Just running the program and testing it works reasonably well for some simple single-threaded programs. But for multi-threaded programs, testing is often completely useless in proving correctness and will at most give you a false confidence. The difficulty arises because there are so many possible execution patterns with multi-threaded code. Often a concurrency flaw may only cause a problem in 1 out of a billion runs, so you simply can't find most raced bugs by running your code. Running your program may find bugs, but it won't find correctness. If your program is buggy, running it might elicit the bug and prove there's a problem. But if your program is actually correct, which I hope it is, running it provides no useful information. Okay, this is a good place to stop. Let me end by saying thanks for watching, and I'll see you in the next video.